Hey guys, the Wild Driver here. So today I just want to go over, or well, really update you on what's going on. So here is IntelliGem, which I'm now calling, I believe I'm going to call IntelliRuby. I'm not sure yet, or maybe I'm keeping it as IntelliGem. I'm not sure yet. Something along those lines. Anyway, so this is it really, which is the CPU core in blue, the DMA controller in green, and then the RAM here. And then up here is just some I/O, so I have a terminal and a keyboard. And down here is the return control from the DMA to tell the little SR latch here to enable the CPU core again. So the idea is the CPU can either have control of the RAM or the DMA access, which means the I/O device that's being controlled by the DMA controller will have access to the RAM. And to prevent collisions where like the CPU is trying to access RAM while an I/O device is doing that, I do the most primitive thing possible and I just tell the CPU core, hey, you're not enabled right now, only the I/O device is enabled and it has access to the RAM, so the clock is only able to enable the I/O device. And then when it returns from the DMA, then the clock is only able to, or the clock is then enabled, the core is then enabled and the clock's able to affect it and increment the program counter, yada yada yada. So I wrote a hello world for it. That was pretty easy. What I'm trying to do now is write a sorting algorithm. So I'd like to, for instance, have the CPU print, hey, enter an amount of numbers to sort, and then the max amount of numbers is, let's say, 99. So that's what I have it saying. And then press enter when done. And so I'd like the user to then press, like 5, 3, or no, that's a lot. Like let's say they enter let's say the user enters 1, 2, and then presses enter. Well, the CPU is going to return on the enter command, and then it needs to convert 1, 2, which is stored as 1 in ASCII, well, UTF-16 ASCII, and 2 in UTF-16 ASCII, and the enter command. So it needs to know the enter command, needs to know that 2 positions have been filled, it needs to know that 1 has to actually be 10 plus the 2. So it has to convert from ASCII to, binary, and then do the BCD conversion. And then now the CPU has a value to work with, right? So like before anything can be even done, like you get these user inputs in, and they're in like these ASCII BCD formats, and you need to convert it from ASCII BCD to binary, like a single binary value. And so like you got to do that, and then I'd like to have the user then enter a bunch of numbers in, like to sort. So if they enter like 156 or 9112, whatever they enter, and I'm going to need this function that does this ASCII to ASCII BCD to binary conversion. I'm going to need to use that function a lot, so I'm going to actually have to write a function that does that pretty nicely. So I'm still approaching that, and the reason I haven't actually done that quite yet is because, well, I asked the guy in my Discord server to help write a linker for me, and part of an assembler that would then allow me to then just define a RAM file that says, like, here, I'll show you. So for instance, here we go. So if I had a message, these are commented out. But let's say I had message 1A, which was, it was a.ASCII-Z, so it's null terminated, and says enter an amount of elements to sort, 99 is maximum. Message 1B is press enter when done, it's also null terminated. And then I'm like reserving 4 bytes of space for the user input. Although I should really be reserving 6 bytes because I need to check for 2 inputs and then the enter, not just 2 inputs. Each input is 2 bytes, so that's why I need 4. Well, that's why I would really need 6 if I wanted to check for 3 values. Anyway, so the ideal thing with the assembler would be able to see that this says .ASCII-Z, and it would know to convert this here to an array of ASCII values that I told him that need to be UTF-16 format. and it would store the base of that array as address message 1A. So message 1A could be address 500 in RAM, right? But then, so that means this is address 500, and this is address 502 after it, because each character requires 2 bytes. Okay, so that's how this works, right? So like the assembler would be able to take this .ASCII, know that this string needs to be converted to a list of ASCII values that are 16-bit, and then stored at the base of message 1A, which the assembler also will figure out. And then the same for message 1B, but I don't have that. So what I had to do is I had to generate the data file here by hand. And how did I do that? Well, I did it was kind of easy, to be honest. But for bigger files, it's going to be a pain in the ass, which is why I need that tool to be developed. Anyway, so you can see here, press enter when done. I typed this in here, and I told it I want a UTF-16 little endian output, where they're 32 bits. Why did I do 32 bits? Why didn't I do 16 bits? There's some reason for that. I don't quite remember what it was. Anyway. Yeah, I don't remember why I did that. But anyway, you can see here is the P R E S S space E N. Oh, sorry for his phone. Okay, sorry about that. As I was saying, we have PRESS space ENTER space WHEN space DONE, and that's how that works. I'm not quite sure why I told it. You know, maybe I should have done this. You know, I don't really understand why I was doing this. Oh well, I think that's definitely what I want, right? Because here's my sorter.hex file. Oh, I'm done. That's why. Yeah, so these are 16-bit values, right? 4 plus 4 plus 4 plus 4 is 16. Oh my god, I'm so dumb. So yeah, that's a UTF-16 value chained together. Yeah, so so I have two UTF 16-bit values chained together to make a 32-bit value at a single RAM word address. And you can see then here is that data file. So what I did, press enter when done, you can see starts right here, PRESS space ENTER space WHEN space DONE, new line feed null character. So that's what that does right there. So before that we should have, oh, that's what's wrong here. Okay, so I want to replace this to 0, 0. I want to change this to 0, 0. Wait, what did I have? This needs to be A0, and this needs to be 0, 0. I want the null character and the new line. That's what's been wrong. Okay, so let me save this. Hopefully now. Okay, so anyway, I've been kind of teasing you guys. I will run this. Hopefully it runs with the right code. Oh, you know what I have to do? First off, so the digital has been bugging out, so like it doesn't run quite very smooth. Like it runs smooth, but like the graphical user interface bugs the fuck out. Anyway, what I think I need to do is then click here, start real-time clock, put in like 100 Hz, and hope for the best. Yeah, it didn't grab the new file, but like, here's what it outputted to the terminal. Press enter an amount of elements to sort 99 as maximum, and then yeah. So what happened before was it did a new line, and then it did a line null character, which put a space. So what it's now doing is going to put a null character, then new line, and then press enter when done should move over like this. So hopefully now, if I... Alright, what I need to do, I will stop recording and I'll get to it. Okay, I still can't get it to work. Don't know what's going on, why I can't get that to display enter properly, but I'm not going to debug that right now. Anyway, so what I figured I'd do is open up the core here. Yeah, I see it's the graphical user interface is bugging out a little bit. So I designed the instruction set to be stupid easy, where the way the instructions work. Give me 1 second, I will pull it up. Boom. Control plus. Okay. So I have these mnemonics, and then the way it works is stupid easy. So like I have a 4-bit operation, 3-bit select, 6-bit source, the destination. Wow. Okay, that needs to be changed. 6-bit source 1, 6-bit source 2, and 32-bit immediate. Anyway, so like for arithmetic 0, 0, 0, 0, I have to tell it what type of arithmetic to perform, and then like here's the operands to perform it on, either RS1, RS2, and immediate, and then sort to RD. So like for example, if I want to do add on arithmetic select, I put in 1. So on here on these 3 bits, I put in 0, 0, 1, and then it would add RS1 plus RS2 to RD, or RS1 plus 32-bit immediate to RD. So you have both options. And that's all in the assembler and on the programmer to choose what to do. So you either use RS2 plus RS1, or it would note that then just use the immediate and RS1, and there would be no RS2 value. Similar thing for logic select, where then I have these logic lines. Okay, so yeah, for arithmetic I have add vector, subtract, absolute value. Logic I have and, NAND, or, nor, XOR, XNOR. For shift, I have shift logical left, shift right, shift left logical, shift right logical, shift right arithmetic, and that's barrel shifting. For SLT, SLTU is set less than and set less than unsigned, which is my comparison, very similar to MIPS and RISC-V. Then I have branch select, where I have these branches, where I have 4 one operation branches, where I say is RS1 equal to 0, is RS1 not equal to 0, is RS1 greater than or equal to 0, is RS1 less than or equal to 0. So it's one operation because, or one operand, because it's always comparing RS1 to 0, so it's just one operand, and then where to go. These are 2 operand branches, which are also very easy to check because they're equal to or not equal to. So RS1 is equal to each RS2, or RS1 is not equal to RS2. So the reason I have these branches is because these are very easy to check for. For instance, checking for equal to 0 is just as easy as ORing all the outputs of a bus together and checking if it's true or not. The same for not equal to 0. Then if it's equal to 0, then it would be not. Then if this is true, then this would be false, and if this is false, if this is true, then this would be false. So these are like inverses of each other. And then greater than or equal to 0, you just look at the sign. Less than or equal to 0, you just look at the sign. So these are inverses of each other. So like really easy. And then like branch of equal to and branch not equal to, these are XORs. So if the XOR is true, then you're equal, and then it's the branch of not equal is false, and then if the XOR is false, then that means branch not equal is true. So you could just off a few gates very easily decide your branches without having to do like subtractions and all that shit. Jump. So jump immediate jumps to the immediate value. It's like absolute. So where the immediate is where the program counter goes. Jump register, it jumps to RS2. JAL RD immediate, so it jumps to immediate and puts the program counter address in RD, which if you don't specify will be the return address register 31. JALer does the same thing, except instead of jumping to the immediate, it jumps to the value held in RS2. Then I have load select, which is like so load byte unsigned, load half unsigned, load word, store byte, store half, store word. And then I have port mapping, so I have 7 ports, 1 through 7, and they're labeled A, B, C, D, E, F, G. And to access them, you just like to load them, you do LPRT, and then A, B, C, D, E, F, G, whatever you want, and then like what register you're loading that port to. And to store, you just store port, and then like you put your RS1, whatever the source value that you're storing to that port. And they're separate ports. So stored port A is not, you can't store port A and then the value won't be on port load. You can't load that back in from port A. Port A and port B, load and store ports are separate from each other, but they share the same names, if that makes sense. Anyway, load DMA select, because you'll never just have the output of one port connected straight to the input of another port without having logic and stuff done in between. Like, it just wouldn't make sense. Anyway, so then now we're on LDMA select and SDMA select. So that's load DMA and store DMA. So this is how I give IO control, their direct RAM access. And so the IO control can either load bytes, load byte unsigned, load half unsigned, load word. So it has full addressing modes like that. and then it could store byte, half, or word. And so here's a little chart I made that puts this all together. Makes it a little easier to digest. So here's the operation. Here's like the register mnemonic, the register RTL, the immediate mnemonic, and the immediate RTL. RTL stands for register transfer logic. So for instance, add RD, RS1, RS2. The logic associated with that is register RD. So if you put in 5 here, then 5, register 5 equals what, and then whatever the source 1 plus source 2 registers are. So like these little brackets are telling you like that's a register, and like you're putting in an address in there, and then that address will be like will contain a value, and that value is what you're adding. You're not adding addresses. If I wanted to say I was adding the addresses, I would say address of RS1 plus the data value in RS2. But no, I want the value in RS1 plus the value in RS2 goes to and writes in the value in RD. If that makes sense. Writes that value into the address RD. So, I hope that makes sense a little bit. Anyway, and then now for the immediate, like I said, for some operations, you can either do either register or immediate formatting. So for all these here, it looks like you can do that, except for absolute value, where it doesn't really make much sense to take the absolute value of an immediate, because you would just put in that immediate of that absolute value already. Because you have a full 32-bit immediate, there's no like restrictions on, there would be no reason to do that. So that really just doesn't make sense there. Like you can do it, it just, like the assembler would let you do it, but for all intents and purposes, it's not an instruction, it doesn't make sense. I know it's a typo here. Boom. Okay. Anyway, so yeah, you can see as we move down this map, it's literally just like operations and what it does and laid out. I can zoom in a little bit and move to the center. Yeah, so you can see here on shift logical left, what it does is it takes RS1 and shifts it left by the amount in RS2. Shift right logical takes RS1, shifts it right by the amount in RS2, and shift right arithmetic takes RS1, shifts it right by the amount in RS2, but preserves the sign. So there's like, I believe this triple shift operator for that. Set less than says if RS1 is less than RS2, it returns true in RD, and set less than unsigned does the same thing. If this is unsigned and is true, then it returns a 1 in RD. And you could do immediate as well with that. Branch of equals, there's no like destination register. There's nothing you're writing back, and what you're always jumping to like an immediate, so I just stuck it over here, but it doesn't really make sense. Like to be in either immediate or register format, it's like neither its own format. Then like jump, oh, and like this is what jump does. Jump just says PC gets immediate. Jump register here says PC equals RS2. Jump and link says PC register destination equals PC, and PC gets the immediate. And then jump and link register, same thing, but PC gets RS2. And then all the load and load stuff, and here's like the port stuff, where you could store a port either like a data value from like a register or straight up an immediate, which is nice. So you have both forms here, but like loading a port, there's no immediate, like there'd be no immediate form, so like that makes no sense. And then yeah, here's the load DMAs here, and then store DMAs here, and that's the mapping for all those instructions. So all those instructions are able to be decoded just by these stupid easy selects that basically in here is just a mux. If I open the circuit. So you can see it literally just is like opcode comes in, which is 4 bits, and then select is 3 bits. And the opcode tells the select where to go. So if the opcode is 0, then select bits go to the arithmetic select. If opcode is 1, then the select bits go to logic select, yada 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 yada. And then here it just decodes out from the opcode. So here's a decoder and there's a mux. So here it just decodes out what op is doing. So now when you come back to here, you can see like this looks very complicated, but it's so simple. And then each one of these logic blocks then has a select input, arithmetic select, logic select, shift select. So all these go into, well, here's its decoders into the ALU, because the ALU deals with all those. But for instance, here's a compare unit, and inside the compare is a compare select, which just tells you, you know, when we have 1, we're doing select set less than, and when we have 2, we're doing set less than unsigned, something like that. And then here's like the branches. If I open up the branches, branch select, it just tells us what branch we're doing. So it just makes the logic decoding so easy for each individual subunit in the CPU. And you can see the branch logic is fucking easy. There's no comparators in here. It's literally just OR gates, AND gates, and we're done. Like, and that's how easy the comparison is. Jump unit, open. jump select, the same thing. I have jump and link, jump register, jump link register, and all these things will then yada yada combine to do what they need to do. But it's very simple, just off the jump select input, because they're all the same format off of that. Load decoder, open circuit. Let's see, load select. Load select here comes out. Oh, I used the built-in digital function that synthesizes logic from an expression. I told it an expression and it generated this. I think I did the same thing with store select as well. Yes, I did. And then like the output ports, I can show you, like they're just a bunch of registers that are available to be seen. And then here are the input ports, which I just like tie to 0 right now because I have nothing, like no input ports being used. I only use 2 output ports for the offset and iteration control and the DMA controller. So you can see all this stuff is stuff going out from the CPU to like everything else to be controlled. So if I exit out of here, that's all this stuff here. So the CPU is going out to control certain things. For instance, it's going to have the port for offset and iteration to then go to the DMA controller to control the iteration here and the offset here. It's going to have LDMA and SDMA, which select, which tells it like what DMA we're doing. Like, so yeah, I guess I should open the circuit. This is going to look a little fucking wacky, but yeah, let's open it. So LDMA select tells me like if I'm loading data in to RAM, or from RAM, LDMA means you're loading from RAM to like the IO device, and store DMA means you're taking from the DMA device and storing to RAM. So the L and S is in reference to the RAM, like what happens to the RAM. So LDMA means we're loading the RAM to the DMA device, store DMA means we're storing the DMA device data to the RAM. And so that's the selection inputs that control it. The enables just pass through, if I call them read and write out the output basically, because that's what's going to happen. If you enable load DMA, we're loading the RAM, and if you enable store DMA, we're writing the RAM. So that's why that's written there, so it could just be passed to the output, so it can be used by the user. And that's all this does really. It just controls all the IO device input and outputs, and digital doesn't like when you have inputs that aren't tied to, you know, something, like you can't just leave them open. So I just tie them all to 0 for the ones I'm not using. I am using one input, which is the keyboard data input, and I am using one output, which is the terminal data output for the DMA devices, which are then these devices here, controlled by the DMA device ID, which I didn't have like a good spot for these, but once I have more devices, I'll put them in a block and stick them up next to the DMA controller. And that's really the whole CPU. So yeah, the goal is to program it to take like an array, or like get the user to input like a set of a number of inputs of values, and then, you know, maybe I would like to have them graphed on the screen. So tell the user to keep them within a certain bound. So if I have like a 1024 by 768 screen, tell them to like keep it within 1024. So like 1023 or less. Generate a bunch of inputs between 0 and 1023, and then it will display them onto the screen, and then each bubble sorting round, it will then update the screen, and you can then see like the waves of this updating across. Like it wouldn't be like a screen hardwired into the program, into the RAM. It would be like a screen, like the CPU would have to tell it to write to the display, probably through DMA. So yeah, I have a lot to think through still, and I need like the software tools to be developed to allow me to do this. But yeah, this is where I am at right now, and I didn't want to like not update anybody on this. This is gonna be a long video, by the way. Holy shit! And yeah, so also I started a new job recently, so I don't really quite have the same time that I used to. Not that I really spent all my time making YouTube videos, obviously, although I did start streaming a lot, so I will try to keep streaming more, especially as the software tools that I need are developed, and I might even start recruiting people on Fiverr to develop the tools that I need, because I'm not a software engineer, but once I have those tools developed, I can continue doing the hardware engineering I need to do. So yeah, that's about it. I appreciate you guys sticking around if you're still here. Leave a like and subscribe. Also, don't forget to join the Discord channel. I'm trying to make it more active. That'd be pretty nice to have a large channel in there, like where we can have like group discussions and people can submit their ideas and whatnot. Anyway, yeah, thanks for watching, and I'll see you guys next time.